We are jumping straight into the data today with a paper called Sekai2, From World Exploration to Interactive World Modeling, authored by Kang He and colleagues from Alaya Lab and Tsinghua University.
Yes, a really fascinating one.
And for those of you out there building video world models, you already know your ultimate bottleneck is training data. I mean, the current landscape forces a pretty brutal compromise.
It really does. You either go for massive scale or high structure.
Exactly. You can train on data sets with massive scale, like WebVid or Panda 70M, but you get these short, heavily edited clips with zero explicit camera trajectories.
Right.
Or you swing to the exact opposite extreme with data sets like Real Estate 10K. That gives you highly structured 3D reconstruction data, but it is tiny in scale and completely lacks sustained, long horizon world evolution.
Yeah, and Sekai2 is engineered to bridge that exact gap.
It drops over 2,800 hours of long horizon real world video where the vast majority are continuous 1 to 2 minute clips. And every single one of those clips is paired with a mathematically explicit camera trajectory and highly granular, temporally grounded semantic annotations.
Which is just wild.
It is. Furthermore, the researchers specifically target the seam forgetting problem in autoregressive models. They do this by engineering a dedicated panoramic subset built entirely around nonlinear routes, loop closures, and spatial revisits.
So to really appreciate why the AI community desperately needs this specific architecture of data, we need to trace the paradigm shift happening in generative AI right now.
Because the goalposts have completely moved.
Exactly. We're no longer trying to generate a visually impressive, isolated 4-second clip of a cat riding a skateboard.
Right. Thankfully, we're past that.
Yeah, the bleeding edge of the field is building interactive world models. Systems like Genie or Oasis.
And for a model to function interactively, it has to maintain a persistent scene state.
Right. It needs to allow for user-driven camera control over an extended time horizon. And the legacy data sets just fundamentally fail at this.
Because they weren't built for it.
Exactly. I mean, WebVid provides immense semantic diversity, but it is essentially a collection of static, descriptive text linked to moving images. There is no mathematical camera path to condition a model on.
Right. And what about spatial vid?
So Spatial Vid offers spatial annotations, but it is heavily biased toward short-range view synthesis, not extended exploration. And then Action 100M is phenomenal for action-centric data, but it totally lacks the sustained structural evolution of a physical environment.
It makes me think of the early days of autonomous driving research. If you try to teach an AI how a physical environment works by feeding it a flipbook of randomized, isolated photographs, you end up with a very superficial understanding of reality.
That's a perfect analogy.
Like, the model might learn the texture of an asphalt road or the shape of a street lamp, but it completely loses object permanence. It loses spatial consistency.
Yeah, absolutely.
When you are generating video token by token, if the model hasn't been trained on how a street corner physically evolves over a continuous 60-second pan, it just hallucinates new, plausible textures instead of maintaining a rigid 3D world.
That hits the core of the problem. If you want a neural network to learn how an environment operates over a full minute of continuous movement, your training diet has to reflect that.
It needs that continuous data.
Right. It has to consist of continuous, minute scale data where the visual content, the physical camera motion, and the textual semantic changes are all perfectly aligned on a shared timeline.
And that structural alignment is the blueprint of Sekai2.
It is. Let's look at the sheer scale of what they've assembled here because it's massive.
Yeah.
The dataset comprises over 128,000 clips, totaling 2,826 hours of footage sourced from 113 different countries.
And I noticed they didn't just scrape the web indiscriminately either.
No, not at all.
They structured the corpus around 3 very distinct locomotion profiles to ensure the model learns different physical mechanics. You have the inherited Sekai subset, which is about 37,600 clips, heavily focused on walking-led exploration.
Yeah, that's the baseline.
Right. Then they introduced the new YouTube subset, adding over 80,000 clips that bring in much faster and more diverse traversal drone footage, driving sequences, rail travel, and cycling.
Which introduces so much dynamic physics.
Exactly. And finally, they built the self-captured panoramic subset, consisting of 982 specialized 360-degree sequences. But what stands out to me as an ML engineer is the temporal scale.
Oh, the temporal length is the defining flex of Sekai2.
It really is.
The average clip length across the entire corpus is 78.9 seconds. When they run their standard 120-second decomposition, over 51% of the total footage comes from clips reaching that full 2-minute maximum.
Wow. 2 full minutes.
Yeah. To put that in perspective, segments lasting at least 60 seconds make up over 92% of the entire dataset. You're feeding the model sustained observation.
Which basically forces it to maintain latent consistency for hundreds of frames longer than traditional training sets allow.
Exactly.
Here is where I have a massive practical concern, though. If I am training an autoregressive model on 2-minute YouTube clips, my biggest fear is editing artifacts.
Oh, yeah, the hard cuts.
Right. YouTube is full of vloggers using hard cuts. If I feed my world model a continuous 2-minute tensor that suddenly jump cuts from a walking shot in a living room to a drone shot over a mountain, the model's physics engine is going to learn that entire environments can instantaneously teleport.
Which would totally ruin the spatial reasoning.
Exactly. Those messy scene shifts would completely corrupt a model trying to learn continuous mass and motion.
Well, the researchers anticipated that exact corruption, which led them to build an incredibly rigorous data engine. They knew they couldn't just rely on raw video.
So what did they build?
They developed a processing pipeline anchored by a tool called OmniShot Cut. The function of OmniShot Cut isn't just to flag that a cut happened.
Okay, what does it do?
It uses visual heuristics to detect both abrupt hard cuts and subtle, gradual transitions, like crossfades. But rather than simply slicing the video exactly at the cut line, the pipeline aggressively removes a full 6-second buffer around those internal boundaries.
Wow, a 6-second quarantine zone around the cut.
Yep, exactly.
That guarantees you aren't catching the tail end of a fade or an overlapping audio-visual transition. You are ensuring the remaining clip represents purely continuous physical state evolution with zero editing artifacts baked into the training weights.
Precisely the goal. But physical continuity is only half the battle, right?
Right.
The visual data also has to be pure.
Right, pure from screen overlays and stuff.
Yeah. The pipeline runs a multi-stage filtering framework to clean the frames. To handle visual purity, they employ EasyOCR alongside edge detection algorithms.
Okay, so EasyOCR for text.
Right. EasyOCR scans the video for text bounding boxes, and the edge detection looks for unnatural static geometric shapes overlaying the footage. This systematically filters out head-up displays from video games, burned-in subtitles, and channel watermarks.
Oh, as someone who has spent hours trying to figure out why my generation model keeps hallucinating a translucent minimap in the corner of a generated forest, that OCR filtering is an absolute lifesaver.
It's so necessary.
Because generative models are incredibly lazy. If they see a watermark in even just 5% of the training data, they will overfit and bake that UI element into the physics of the world.
They will. By stripping those out, you isolate the actual environment. But the pipeline doesn't stop at visual artifacts. It also filters for motion density.
Motion density meaning how much things are moving.
Yeah. If a model trains on 2-minute clips of a completely static security camera, it wastes compute and biases the generation towards zero movement. To solve this, they use RAFT small.
Oh, right. RAFT.
For anyone unfamiliar, RAFT stands for Recurrent All-Pairs Field Transforms. It is a deep learning model that computes optical flow, essentially calculating how every pixel moves from one frame to the next.
Right, measuring that pixel shift.
Exactly. By measuring that optical flow, they can automatically discard scenes that lack meaningful camera or subject motion.
But wait, if they aggressively filter out static scenes using RAFT, aren't they introducing a new bias?
How do you mean?
Well, a world model needs to know how to stand still. If it only ever trains on heavy motion, you risk a model that constantly drifts or forces the camera to pan just to satisfy its training distribution.
That is a critical vulnerability, yeah, and the team accounted for it brilliantly. While they filter out degenerate, entirely static clips, they deliberately curate and save a 6% low-motion recovery branch.
Oh, smart.
Very. This subset is reintroduced into the final dataset. It acts as an anchor, ensuring the dataset remains balanced so the model learns how to represent stationary observation without hallucinating artificial drift.
So if we step back and look at the pipeline up to this point, we have produced perfectly continuous, visually clean, motion-balanced 2-minute video clips.
Exactly.
But here's the reality of multimodal training. Perfectly clean video is useless if the text embeddings describing it are a tangled mess.
100%.
If a caption just says, "A woman walks down a street," the model is left guessing. Is the camera following her? Is the camera static while she walks past? Is it a drone shot? Without precise text, the model can't untangle the subject's movement from the camera's movement.
Which brings us to the hierarchical annotation schema. This is the layer where Sekai2 truly distinguishes itself from legacy datasets.
Yeah, let's get into the text processing.
The researchers deployed a massive vision language model pipeline utilizing Kimike 2.6 to generate nearly 650,000 temporally grounded semantic segments.
Wow.
Yeah, instead of writing one global caption for a 2-minute video, the AI evaluates the visual evidence and fractures the video into discrete 10 to 20-second intervals based on structural shifts in the footage.
But what triggers the VLM to create a new temporal boundary? They can't just be arbitrary timestamps, otherwise you'd cut a semantic action in half.
No, the boundaries are completely dictated by the scene's evolution. The pipeline creates a new interval whenever a salient new element enters the frame, when the global illumination significantly changes, or, most importantly, when the camera fundamentally shifts its behavior.
Like transitioning from a forward dolly to a static pan.
Exactly. And once the interval's locked, the text labels are explicitly factorized into 4 distinct buckets. First is subject motion, detailing the main agent's activity.
Okay, got it.
Second is environment motion, which captures peripheral moving entities like passing cars or background pedestrians. Third is the static scene, describing the persistent architectural layout, lighting, and materials.
And the fourth?
The fourth bucket is the camera description, which rigidly isolates the viewpoint, framing, and stability.
You know, I look at that factorization and it instantly reminds me of a well-formatted movie script.
Oh, how so?
Well, when you read a screenplay, the dialogue and the character actions, like the reality of the scene, are explicitly separated from the stage directions that tell the director of photography what to do.
That's a great way to put it.
You never mix a character's emotional breakdown into the same sentence that dictates a 50mm lens pull. The VLM is doing the exact same thing for the neural network.
Yeah, and that separation is vital for training flexibility. To make this data actionable for engineers, the pipeline takes those factorized labels and synthesizes 2 distinct training prompts for every interval.
Okay, how are they different?
You get the full prompt, which integrates all the buckets, but explicitly isolates the camera behavior inside XML-style camera tags. Then you have the short prompt, which completely strips out the camera tags, leaving only the environmental description.
Oh, I see.
This dual prompt system allows researchers to dynamically drop, replace, or heavily weight camera conditions independently during their training runs.
That is fantastic for text conditioning. I can tell the model, pan left using a camera tag, but if we are genuinely building interactive world models where a user might plug in a joystick, text tags alone are insufficient. Words won't teach a neural network the mathematical geometry of a 30-degree rotation. We need to ground those descriptions into actual 3D space.
And that requirement pushes us straight into the geometric supervision layer of Sekai2. Every single clip in the dataset includes an explicitly calculated camera trajectory.
That sounds computationally heavy.
Oh, the pipeline to generate this is massive. They start with GeoCalib, which analyzes the raw pixels to estimate the camera's intrinsics, meaning it mathematically deduces the focal length, lens distortion, and field of view without needing the physical camera metadata.
Wow, just from the pixels.
Yep. Then they feed those intrinsics into VIP for initial pose estimation, and finally optimize the entire trajectory using Droid SLAM.
Okay, and for those catching up on the robotics terminology, SLAM stands for Simultaneous Localization and Mapping.
Right.
Droid SLAM is a deep learning architecture that tracks how individual pixels move across sequential frames. It uses that dense optical flow to build a rigid, mathematical 3D map of the camera's exact trajectory through the space, providing a transformation matrix for every single frame.
Exactly. And by supplying that transformation matrix, the math sits right alongside the XML text tags.
So it's not just language anymore.
Right. The model doesn't just read pan left, it ingests the exact quaternion rotation and translation vectors associated with that movement.
Which perfectly sets the stage for the biggest hurdle in autoregressive generation and, honestly, arguably the most important contribution of this paper. Solving scene forgetting.
Oh, absolutely.
We've got the factorized text, we've got the 3D SLAM map, but none of that natively fixes a model's short-term memory, right?
No, it doesn't. Scene forgetting is the absolute bane of autoregressive architectures. Because these models generate the next frame based primarily on a limited context window of recent frames, they lack long-term spatial memory.
They just forget what they saw.
Right. Picture a virtual observer walking down a hallway. They reach the end, turn around 180 degrees, and the model, having flushed the initial hallway from its immediate visual context, hallucinates entirely new geometry behind the observer.
Like the door they just walked through vanishes, replaced by a random window?
Exactly. It is a complete failure of object permanence.
And if you are building a video game or a robotic simulation, the environment must be persistent. If I turn around, the physics of the world demand that the geometry I just passed is still there, exactly as I left it.
Standard web video cannot train this capability. I mean, linear YouTube drone shots or forward-facing dashboard cameras rarely feature sustained, controlled revisits to a previous location from a new angle.
So what did they do to fix this?
To force a model to learn spatial persistence, the Sekai2 team went out and physically captured their crown jewel subset. 982 panoramic 360-degree sequences, totaling 119 hours of highly specialized footage.
Okay, but how does capturing footage in 360 degrees change the training dynamics for an autoregressive model?
Well, the hardware is really only part of the solution. The real value is in the traversal strategy. The team explicitly recorded these sequences along nonlinear routes, heavily featuring complex loops and spatial revisits.
Oh, so they intentionally walked in circles.
Essentially, yes. Because the camera captures a full 360-degree sphere of visual data, the surrounding context is never fully off-screen. But the critical engineering step happens during the data processing. They subject this panoramic data to loop closure trajectory refinement, a technique known as pose graph optimization, or PGO.
Okay, let's unpack PGO for a second. When you run a SLAM algorithm over a long period, microscopic mathematical errors compound, right? The system drifts.
Yes, exactly.
So PGO is the corrective measure. When the camera revisits a location it saw 5 minutes ago, the system recognizes the visual overlap, creates a loop closure, mathematically snapping the trajectory back into alignment, correcting all the accumulated drift along that path to lock down a globally accurate map.
You nailed it. And by providing geometrically verified loop closures, you offer the neural network the ultimate object permanence test. The model is forced to maintain a persistent 3D spatial memory over several minutes of video.
That's incredible.
It is. When the camera loops back, the AI cannot just guess or hallucinate the next frame based on the text prompt. It is mathematically constrained to render the exact physical space it previously observed. This transitions the architecture from a simple pixel texture generator into a full-on spatial reasoning engine.
But anytime a data set relies this heavily on automated pipelines, using Kimi for the text, RFT for the motion, and Droid Slam for the trajectories, you run into the ultimate ML engineering question.
Right. Is it accurate?
Exactly. How do we know this auto-generated data isn't just hallucinated garbage? If the Droid Slam labels are slightly wrong, the world model absorbs that error as its ground truth for physics.
The authors knew the community would demand proof, so the validation section of Sekai2 is exceptionally rigorous. They applied intense cross-modal and geometric validation to prove that all these automated modalities actually align.
How did they test the geometry?
For the geometry, they utilized ground truth-free epipolar validation. They calculated the Sampson error between corresponding points and frames separated by half a second using the fundamental matrix derived from the released camera poses.
The Sampson error is a brilliant metric here. For those who haven't worked with multi-view geometry, imagine a geometric tether between where a pixel is in frame 1 and where the math dictates that pixel must live in frame 2 based on the camera's movement.
Right, the theoretical line.
Yeah. The Sampson error simply measures the physical distance in pixels between the actual visual feature and that theoretical mathematical line. If the SLAM math is wrong, the distance gets huge.
And the results prove the math was right. For the inherited subset, the median Sampson error was an astonishingly low 0.12 pixels.
Wow.
Yeah. And for the newly collected subset, using a very conservative fixed focal protocol, it was 0.43 pixels. The generated camera poses a line with the actual visual image pairs almost perfectly.
My absolute favorite part of this validation, though, was the negative control they ran. They didn't just test the correct math, they deliberately sabotaged their own pipeline to see if the system would catch the error.
Yes, the mismatched pose test.
Right. They took the exact same visual image pairs and the exact same temporal intervals, but they artificially shifted the camera pose pair by about 1/3 of the trajectory. They basically handed the math the wrong slice of the right camera path.
And the results of that sabotage were definitive. When they mismatched the poses, the median error spiked massively, up to 23 times higher in some cases, hitting 2.83 pixels.
Which is huge in this context.
Huge. That spike acts as a perfect negative control. It proves that the incredibly low error rates in the actual data set aren't just a fluke of the image content or a lazy algorithm. The low error specifically validates their exact frame-by-frame pose alignment.
They also ran a cross-modal audit to ensure the text matched the math, didn't they? I mean, it's one thing for the SLAM to be accurate, but if the VLM wrote the wrong caption, the model still learns the wrong associations.
Yeah, the cross-modal audit is the final piece of the puzzle. They checked whether the discrete text labels from the Kimi VLM actually matched the continuous mathematical vectors from the droid SLAM trajectories.
Like matching the words to the math.
Exactly. For instance, if the VLM labeled an interval with the text "turn left," the validation script checked the measured yaw change in the VPE trajectory for that exact same time frame.
And it held up.
Completely. The math completely corroborates the text. Segments labeled as turning exhibit significantly larger yaw changes than segments labeled as straight motion. The text embeddings in the 3D geometry were independently derived by completely different AI systems, yet they tell the exact same physical story.
Which means researchers can actually deploy this dataset with complete confidence. You aren't feeding your massive GPU cluster noisy, unverified slop. You are feeding it mathematically verified, temporally grounded, physically persistent representations of reality.
And that really brings us to the broader implications for anyone working in AI today. We are crossing a definitive threshold in the industry right now, with data engines like Sekai2 providing this magnitude of explicit multimodal supervision. The objective function has evolved.
It really has, and it leaves you with a really provocative thought to mull over as you look at your own projects.
What's that?
Well, if an AI architecture can accurately predict long-range spatial revisits, and if it can maintain the physical state evolution of a complex environment over minutes of non-linear camera movement, at what point does a video generator cease being a simple media creation tool?
Oh, that's a great question.
Right. Once a model mathematically understands that turning the camera 180 degrees means rendering the exact 3D geometry you just left behind, it is no longer just painting pixels. It is functioning as an interactive digital twin of reality. The boundary between video generation and physics simulation is collapsing.
It absolutely is. And when that boundary fully collapses, the applications for robotics, autonomous navigation, and procedural virtual environments become virtually limitless. The ceiling for world models just got exponentially higher.
It certainly did. Well, that wraps up our breakdown of the Sekai2 paper. As a reminder to everyone, you are tuning into the AI Paperslop YouTube series, where we break down the research defining the future of tech. Keep your eyes on the horizon, and definitely go check out the Sekai2 GitHub repository to pull the actual data for your own models. Catch you on the next one.